My name is Diego Salazar, and I'm the project manager for Victory Engineering. We were provided with this super project called the State Road 836 extension that will go from 137th Avenue all the way down to 136th Street. Just to talk about the project, we all know that the southwest region of Miami-Dade County has grown exponentially, and it is said that it's going to grow to an 83% by the year 2030. With this expansion in population, we can expect, low developments with housing, supporting businesses, schools, services. The 836 extension is going to provide that needed highway for people and future generations that are going to live in this area, so that they can commute and connect with other parts of the county as well. With that being said, let me just introduce my team. Like I said before, my name is Diego Salazar. I'm the project manager and structural engineer. Emil Mateo is our geotechnical engineer. Kevin Love is in charge of our environmental. Fritz is in charge of our construction management program. Ana Puebla is our transportation engineer. And Adrianis Martinez is our geometric design engineer. I'm gonna pass it over to Ana, and she's gonna better explain what the project is about.
Good evening. Once again, my name is Ana Puebla. I'm the transportation specialist for this project. As Diego mentioned, the purpose of this project is to relieve traffic and provide a valid mobility option. We'll be extending the existing State Road 836 from Northwest 137th Avenue all the way south to Southwest 136th Street in West Kendall. The length of this project will be about 14 miles. This is the alignment. It will run first parallel and north of 8th Street, and then will run parallel and east of Crown Avenue. This will include 7 bridges. The first one will cross a canal on Northwest 145th Avenue. The second one will cross another canal on Northwest 147th Avenue. The third one will cross Southwest 8th Street, and bridge number 4, 5, and 6 will interchange Southwest 42nd Street, 88th Street, and 104th Street. And we're gonna extend Southwest 42nd Street and 104th Street to connect with Chrome Avenue. The last bridge will cross another canal that is in Southwest 112th Street. Victory Engineering will prepare all plans and specification in accordance with the DOT, PBM, and AASHTO design standard. The design speed for the main line is 60 miles per hour. For the ramps, it's gonna be 30 miles per hour. And this project will improve the level of service on Southwest 88th Street and Southwest 42nd Street. The expected traffic volume for the same year will be 36,000 vehicles per day. This is gonna be the typical section for the main line at ground level. We're gonna have 2 12-foot lanes in each direction, going southbound and northbound. We're gonna have 8 feet inner shoulders and 12 feet outer shoulders. Keeping in mind that this area will continue to grow in population, we decided to have a 60 feet median to accommodate additional lanes in the future. This is the typical interchange that is going to be on 42nd Street, Southwest 88th Street, and Southwest 104th Street. It's called partial clear leaf, and this interchange will only require traffic lights at the exit ramps to turn east or west. Now he's going to explain about the design.
Good evening, my name is Adyanis Martinez and I am the geometric design engineer for this project. According to the PPM manual and based on our design criteria for this roadway extension, we are going to have a maximum grade of 3% for mainline and a 7% for the ramps. As Ana and Diego mentioned on previous slide, we are going to have 7 bridges, which they will have a minimum vertical clearance of 16 feet 6 inches. The maximum curvature for the main line of this roadway will be of 3 degrees and for the ramps will be of 24 degrees. Using the table 2.7 on the PPM manual, we got a minimum stop inside distance between 613 feet and 673 feet for the ramps, and for the ramps will be 182 feet to 218 feet. Now, for safety purpose, that is one of our major concerns on this project. The length of horizontal curvature that we are going to use is 1,800 feet in the turning section that will end at the intersection with 136th Street. Light poles are going to be placed along the outside shoulder of the roadway on both south and northbound direction, every 250 feet, and totaling of 700 poles. The model chosen was the Hessia MIDI light and is the best to illuminate the roadway. The poles are made of aluminum cast and are able to withstand winds of up to 150 miles per hour.
Hello again, I'm going to talk about a little bit about our structures, the designs. Based on AASHTO load and the resistance factors, we came up with 2 bridge designs. One is going to be a box girder post tension design, and the other one is going to be a crossover bridge that mainly is going to service canals and most intersections. Our most challenging cross-section or interchange would be at 8th Street. This is because it's a longer span of a bridge, and for that reason, we have decided going with the concrete box girder, which is going to have a 340 feet span, and it's going to be about 170 feet on each. It's going to be 340 each in length, and it's going to have 170 feet in within each span. As Dr. Martinez already mentioned, we were thinking about using a it's called a balanced cantilevered construction method, which is going to require a country to develop it and erect it. The superstructure for this bridge, it's going to consist mainly on high strength concrete. It's obviously going to be a concrete box girder. It's going to have wire strands that are going to have a dimension of about 1/2 inch. It's going to be post tension. Like I said before, it's going to have each span is going to be about 170 feet. It's going to be anchored and obviously going to have a substructure made of mid steel. It's going to be a hammerhead pier, reinforced with normal concrete, and it's also going to have pads to sustain. Here it's a video, and I hope you can see it, and it's going to show exactly how it's going to be erected, or at least we'll give you an idea. I know you've seen it before on the 836 and Palmetto interchange, but it's basically the same idea that we're proposing for this bridge right here. As you see, the gantry rests on the columns, and for purposes of this bridge and this project, we would not be able to have as many columns, so we're going to have to use a false work to sustain the bridge and be able to construct it. I think that's enough for our segmental bridge. Obviously, the bridge is going to be, it's going to have loads, and some of those loads are described here as dead loads, superimposed loads, live loads, wind loads, braking forces, impact loads, and obviously the gantry has to be taken into consideration. Here's a depiction of the shear diagram, and you can see that most of the shear forces are going to be concentrated on their supports, the ends, and obviously the pier that we're proposing for this flyover. This is a moment diagram that will show you that most of the moments are here at the mid-span of each of the spans, and that's where our greatest moment is going to be located. If we go over to the next section, this is our pre-stressed, pre-cast concrete beam bridge. It's going to be about 180 feet long. It's going to have a span of 90 feet on each side, and it's going to be supported on a multi-column pier. The superstructure is going to be a pre-stressed, pre-cast concrete girder, continuous bridge deck, which is about 8 inches thick. It's going to have barriers. The substructure is going to consist of a multi-column pier, pier footings, and pile foundations. Again, this bridge is going to be subjected to dead loads, superimposed loads, slide loads, wind loads, braking forces, and impact loads. Let me just stop for a second and better explain the construction method that we're going to use for this bridge is going to be different than from the other one. For this one, we're going to be using a heavy lift construction method, and it's going to be we're going to be using pretty much jacks and cranes to actually erect it. The reason that we are using that method is because of rotations that we can be subjected in the near future in case that we don't have enough space to construct it. This is the beam. This is the singular beam and beam moment and shear diagram, and you can see that this is pretty much depicts our live loads as it goes through the beams. With that being said, I'm just going to pass it over to Kevin Love, and he's going to explain our environmental issues.
Hello everyone, thank you for this opportunity to speak to you guys. My name is Kevin Love and I am the environmental engineer for Victory Engineering. And before I get into depth into some details in regarding drainage, we understand that we have to reach out to certain agencies so that we can acquire the appropriate permits, so that we can obtain the knowledge, so that we can move forward with the process and basically ultimately finishing this project. So what we have here, if we take a look in the upper left corner, we have our corrugated pipe. And if we take a look to our upper right corner, we have our catch basin. And in the middle, it depicts what it actually is supposed to look like in regards to the ballastine rock, serving its purpose to prevent settlements from going to the pipe and entering the drainage system. And it's also supposed to extend the longevity of the pipe as well, to prevent it from cracking or breaking it or anything like that. If we take a look at the bottom two pictures on the left and the right, you see we have our freestanding pipe, which will be connected to our bridges and allow for and alleviate the rainfall runoff as well in regards to rainfall for the bridges. And just going back a little bit, in regards to our archaeological discoveries, here at Victory Engineering, we understand what the environment means to us, and our motto is environment today, planet tomorrow. So it's very important that we understand, here at Victory Engineering, we understand and we respect the archaeological and historical sites anywhere we do construction. So with that being said, we had our engineer of record reach out to the Florida Historic Preservation Office, and they pulled up some files of where prehistoric middens may be and burial grounds. And being that it's not in the critical path of construction, we didn't have too many issues regarding that. But what was very important, based on the critical path we chose for construction, was the actual Miccosukee Resort and Gaming Lounge. And that's important because in order to do construction there, you have to meet with consultation with the head chief there in order to proceed. And through various meetings and long hours, we were able to get the confirmation to proceed with construction in that area. Now, what I want to speak on a bit is the stormwater prevention pollution plan. But before I get into that, I would like to speak about two of the more dominant surface waters in the scope of this project. C-1W, which is the Black Creek Canal, and C-4, which is the Tamiami Canal, and they're more towards the north and south of the project. And these canals are important because they're used for drain water to the southeast coast Atlantic and through the South Florida Water Management District. And these canals provide flood protection, drainage, and supply water to the Bird and Dry Basin as well. And our stormwater pollution prevention plan will consist of filter fabric that will be placed in the drainage systems to help prevent turbidity and soil from entering the drainage system. To add, Victory will also include portable wash racks to rid any soilage or anything like that from the trucks moving forward with the process. And in regards to air quality, to ensure the air quality in the area of this project, Victory Engineering, we created an air mitigation plan, and this will reduce the effects of contaminants harming the air quality at our construction sites. In order to be successful, we have implemented adding coverings to all trucks entering and exiting the site of construction. We have also, to implement, we got a double whammy with this one, for the portable wash trucks. In order to wash off the tires, we also reduce the level of contaminants going into the air as well. And finally, we will periodically wet the site so that we can also eliminate poor air quality. Lastly, we will deploy low emission equipment, and by doing this, we will reduce the power that we're using and ultimately reduce the cost of the project. In regards to noise, we have identified the sensitive areas of this project, and because we're so far west, we don't really have to focus on it too much, but more towards 8th Street where there are more businesses and the actual level of traffic is quantified, we have reached the appropriate need for noise abatement measures in that area. Lastly, Victory Engineering believes in building peace with endangered species in the area, and we have made great efforts to protect all habitats from any negative construction. In this regard, we have all potential debris from construction will be controlled from falling into canals and potentially polluting the water and even potentially hurting the animals themselves. And to give an example, we are aware that the West Indian manatee is is on the endangered list for South Florida. So we will put culverts on our. We will be using culverts to prevent them from getting stuck into them or getting hurt in any way possible. Victory Special Inspection Project Team will ensure that endangered species are safe during construction. And being that I gave a little bit of information about our environmental aspect, we will move forward into the geotechnical.
Hello everyone, my name is Emil. I'm going to discuss the geotechnical aspect and also a little bit of the flexible pavement design we opted for and discuss the characteristics and why we chose it. It was discussed earlier, but in terms of our alignment and the alignment within the scope and the natural terrain that is existing right now, is composed of highly organic and plastic soils, a lot of wetlands and mucks, and what is considered unsuitable soils, but there is some sandy soils that can be modified to reach a suitable state. AASHTO uses a classification standard from A1 to A8, with the number letter A-8 being the highest plastic limit. So after cone penetration test and soil samples were studied, it was determined this ranges between A6 and A7. Anything above A7 are considered 50% or more of liquid limit, so they are highly plastic, but some can be modified. As it was mentioned before, we're going to use for our design standards